In the winter of 1943, Allied bomber crews flying over the coast of occupied France faced a problem that seemed impossible to solve. Far below them, protected by walls of reinforced concrete, thicker than any armor ever built, the German Kriegsmarine's submarine fleet rested in perfect safety. These weren't ordinary buildings. They were fortresses engineered to withstand anything the Allies could drop from the sky. Conventional bombs bounced off like pebbles thrown against a mountain. 7,000-pound high-explosive weapons, the heaviest munitions available at the time, struck those massive roofs and detonated harmlessly on the surface, leaving nothing but scorch marks and frustration. The U-boats inside continued their deadly work, slipping out into the Atlantic to prey on the convoys that kept Britain alive. The submarine pens stretched along the Bay of Biscay in captured French ports like Lorient, Saint-Nazaire, Brest, and Bordeaux. Each installation represented a triumph of German engineering and a nightmare for Allied planners. The Germans had designed these structures with diabolical cleverness. The roofs weren't simply thick slabs of concrete. They were complex, multi-layered systems designed specifically to defeat aerial bombardment. Some pens featured what the Germans called a Fangrost, literally a bomb trap, consisting of inverted concrete U-shaped beams set on parallel slabs. Above this sat an explosion chamber, then another layer of concrete, then a triangular void formed by tilting concrete beams against each other. If a bomb somehow penetrated the outer layers, the explosion would be contained and redirected, dissipating its force before reaching the submarines below. The total thickness of these defensive layers reached up to 25 feet in some locations. As the war progressed and the threat of more powerful Allied bombs became real, the Germans added even more protection. At Bordeaux, engineers fitted a second roof above the existing 12-foot thick structure. This additional layer measured 7 feet thick and was reinforced with massive blocks a meter wide and 2 meters deep. The design was brilliant in its simplicity. Any armor-piercing bomb would detonate when it struck the upper layer, exploding harmlessly in the void between the two roofs rather than penetrating into the main structure. If you're finding this story as fascinating as we hope, please take a moment to hit that like button and subscribe to the channel. Your support helps us bring you more incredible true stories from history. And drop a comment below letting us know what you think about these engineering marvels. Between January and February of 1943, the Royal Air Force and the United States Army Air Forces launched a massive bombing campaign against Lorient. They dropped nearly 150 tons of explosives on the submarine pens. The bombs destroyed virtually everything else in the city. The pre-war population of 46,000 was reduced to just 500 people. Admiral Karl Dönitz, commander of the German U-boat fleet, surveyed the devastation and remarked with grim satisfaction that not a dog remained in these towns. Nothing was left standing, but the U-boat bunkers survived intact. The submarines continued operating without interruption. The problem was clear. Conventional aerial bombardment, no matter how massive, could not crack these concrete fortresses. The Allies needed something revolutionary, something that conventional military thinking had never conceived. They needed weapons that didn't just explode on impact, but penetrated deep before detonating. They needed bombs that could punch through concrete like it was butter. The solution came from an unlikely source, a brilliant and eccentric British aeronautical engineer named Barnes Wallis. Today, Wallis is perhaps best remembered for his bouncing bomb used in the famous Dambuster raids of May 1943. But his most significant contribution to defeating Germany's submarine threat came from a different concept entirely, what he called the earthquake bomb. Wallis understood something fundamental about destroying hardened structures. You didn't necessarily need to hit them directly. If you could create a localized earthquake effect by detonating a massive explosive charge deep underground near the target, The shock waves would do what surface explosions could not. The structure would be shaken apart from within or shifted off its foundations. But to achieve this effect, the bomb needed to penetrate deep into the earth before detonating. And to penetrate that deep without breaking apart, the weapon needed to be fundamentally different from any bomb ever built. Wallace designed his earthquake bombs to be aerodynamically perfect, long and slender like enormous artillery shells. They were cast from a single piece of high-tensile steel, strong enough to survive slamming into the earth at terminal velocity without shattering. When dropped from extreme altitude, these weapons would accelerate to speeds that conventional bombs could never achieve. The first of these revolutionary weapons was the Tall Boy, weighing 12,000 pounds, 5 long tons of precisely engineered destruction. It could only be carried by specially modified Avro-Lancaster heavy bombers. The Tall Boy proved so valuable that RAF crews were ordered to bring them back to base if they couldn't drop them on target, rather than jettison them into the sea. The risk to the air crews of landing with a live bomb aboard was considered acceptable given the weapon's strategic value. When Wallace discovered that the Lancaster could be modified to carry something even larger, he created the Grand Slam, a 22,000-pound monster that represented the ultimate expression of his earthquake bomb concept. This was the largest and most powerful conventional aerial bomb used by any nation during the entire war. An RAF officer who inspected the crater left by one of these weapons found himself staring into a hole 70 feet deep and 130 feet wide. The target building, located 250 feet away from the impact point, was seen to physically move when the bomb detonated. But even as Wallace perfected his earthquake bombs for use against bridges, viaducts, and railway tunnels, the U-boat pens presented a special challenge. These weren't targets where near misses would suffice. The pens sat in heavily populated port areas where creating massive earthquakes would cause unacceptable collateral damage. What was needed was a weapon that could penetrate the concrete roofs directly, drive deep into the structure, and detonate inside the pens themselves, destroying the submarines in their protective shells. The inspiration for this weapon came from the most unexpected place imaginable. In 1943, Walt Disney Studios released an animated propaganda film called Victory Through Air Power. The film advocated for strategic bombing and featured animated sequences showing various bombing concepts. One sequence in the Disney film depicted a rocket-assisted bomb that could accelerate after being dropped, achieving velocities high enough to penetrate heavily fortified targets. It was an animator's fantasy, but to the engineers of the British Royal Navy, it was a blueprint for a real weapon. The Royal Navy's designers set to work creating what would officially be designated the 4,500-pound concrete-piercing rocket-assisted bomb. But everyone who worked with it called it by a simpler name that honored its inspiration. They called it the Disney bomb, or sometimes the Disney Swish. And when Allied bomber crews saw what this weapon could do to concrete that had been considered impenetrable, they called it something else. They called it Witchcraft. The Disney bomb was unlike any weapon that had flown before. It was engineered according to principles derived from Newton's approximation for impact depth and an empirical design equation known as Young's equation. These formulas indicated that maximum penetration required a projectile that was dense, long, thin, and traveling at the highest possible velocity. The Disney bomb embodied all these characteristics. It was much slimmer than conventional aerial bombs, giving it exceptional sectional density. But its revolutionary feature was the cluster of rocket motors attached to its tail. Here's how the weapon worked. A bomber would release the Disney bomb from altitude, typically around 15,000 feet. The bomb would fall freely, accelerating under gravity like any conventional munition. But at 5,000 feet, the rocket motors would ignite. For 3 seconds, those rockets would burn, adding 300 feet per second to the bomb's velocity. By the time it struck its target, The Disney bomb was traveling at 1,450 feet per second, nearly 1,000 miles per hour, approximately Mach 1.29. At that speed, the weapon would slam into reinforced concrete and simply keep going, punching through barriers that would stop any conventional bomb. The penetration capability was almost unbelievable. Post-war testing demonstrated that Disney bombs could penetrate concrete roofs nearly 15 feet thick. Engineers calculated that under ideal conditions, the weapon could penetrate more than 16 feet of solid concrete before its fuse-triggered detonation. Inside that aerodynamic steel casing was 500 pounds of shellite explosive. The bomb would drive through the protective layers that the Germans had built at such enormous expense, through the Fangrost and the explosion chambers and the reinforced slabs, and finally detonate deep inside the structure where it could do real damage. But creating this revolutionary weapon was one thing. Using it effectively was another challenge entirely. The Disney bomb was so long, 17 feet from nose to tail, that it wouldn't fit in the internal bomb bay of standard bombers. American B-17 Flying Fortresses had to be specially modified to carry Disney bombs on external wing racks, with 2 bombs mounted between each inner engine and the fuselage. This external mounting created aerodynamic challenges and made the aircraft more difficult to fly. And because the bombs were rocket-assisted, there were inevitable reliability issues. The rocket motors experienced high failure rates, and without the additional velocity they provided, the bombs couldn't achieve their designed penetration capability. Moreover, accuracy remained a persistent problem. The U-boat pens were relatively small targets surrounded by civilian areas. Dropping from high altitude with sufficient precision to hit these hardened structures proved difficult even for experienced bombardiers. A bomb that missed its target, no matter how sophisticated its design, accomplished nothing. The Disney bomb saw its first combat use in early 1945, very late in the war. By this time, Allied ground forces were advancing across Europe, and many of the U-boat pens in France had already been captured or rendered irrelevant. But the weapon was deployed in several operations against remaining German naval facilities. On March 14, 1945, 3 B-17 Fortresses attacked the E-boat pens at IJmuiden in the Netherlands with Disney bombs. Additional strikes were conducted through March and April of that year. In total, 158 Disney bombs were deployed by B-17 bombers during 4 combat missions. The results were mixed. When the bombs functioned as designed, hitting their targets with rockets firing properly, they demonstrated excellent concrete penetration capability. They could do what the title of this story promises, punch through U-boat pens like butter. But the high rocket failure rates and accuracy problems meant that many bombs failed to achieve their potential. The explosive fill of only 500 pounds was relatively small for such a large weapon, and if the bomb struck a secondary structure or debris, its case sometimes lacked the strength to survive and continue penetrating. The weapon had arrived too late, and in too few numbers, to significantly impact the outcome of the war. Meanwhile, Barnes-Wallace's Tallboy and Grand Slam bombs were achieving spectacular successes against other types of hardened targets. These weapons were used to destroy massive concrete structures that conventional bombing had failed to damage. One particularly dramatic operation targeted a U-boat pen under construction at a site that the Germans called Valentin, located on the Weser River near Bremen. The RAF had monitored this facility during its entire construction, taking aerial reconnaissance photographs at every stage of development. When the bunker was finally completed, British planners knew exactly where the concrete was thinnest and most vulnerable. They struck the facility with precision just as construction finished, hitting it in exactly the weak points they had identified. A Grand Slam bomb penetrated the reinforced concrete roof and detonated inside, causing catastrophic damage. After the war ended, Allied engineers conducted extensive testing to understand the effectiveness of various weapons against massive reinforced concrete structures. The abandoned U-boat pen called Nordsee 3 and subterranean bunkers on the island of Heligoland became test sites. Avro Lancasters from No. 15 Squadron RAF and American Boeing B-29 Super Fortresses and B-17 Flying Fortresses flew approximately 140 sorties, dropping a range of different bombs against these practically indestructible targets. The tests included American versions of British earthquake bombs and various concrete penetrating designs. The main conclusion of what was called Project Ruby was sobering. Not any of the bombs tested were suitable for use against massive reinforced concrete structures of the type the Germans had built. This conclusion might seem to contradict the success stories of weapons like the Disney bomb, the Tallboy, and the Grand Slam. But the reality is more nuanced. These weapons could damage and sometimes destroy reinforced concrete targets under the right circumstances, but they couldn't reliably and consistently demolish structures built to the specifications of the German U-boat pens, not when those structures featured multiple layers of defense, explosion chambers, and roofs up to 25 feet thick. The Germans had simply built their submarine fortresses too strong for the bombing technology of the era to guarantee destruction. Yet, in another sense, the entire effort to destroy the U-boat pens became unnecessary. The Atlantic battle turned against the Germans not because their submarine bases were destroyed, but because of a combination of other factors: improved Allied convoy tactics, long-range aircraft coverage, better anti-submarine weapons, and, critically, the breaking of German naval codes allowed the Allies to route convoys around U-boat positions and hunt the submarines at sea. By the time weapons like the Disney bomb were ready for combat use, the U-boat threat had already been largely neutralized through these other means. The irony is that while the massive Allied bombing campaigns failed to destroy the U-boat pens, they did accomplish something strategically valuable, though at terrible cost. The bombing devastated the surrounding French port cities. Hundreds of civilians lost their lives in these raids. Entire urban areas were reduced to rubble. This meant that when U-boat crews returned from patrol, they found their bases intact but everything around them destroyed. There were no facilities for rest and recreation, no intact infrastructure to support operations, no civilian workforce to maintain equipment. The bases became isolated islands of concrete, in seas of destruction, functional but increasingly difficult to operate from. Today, those same U-boat pens still stand along the French coast, monuments to the engineering capabilities of their builders and the limitations of even the most advanced weapons of their era. The bunker at Lorient has been transformed into a 50-acre development called La Basse, featuring restaurants, museums, and educational facilities. Visitors can walk through the massive concrete structures and try to imagine what it was like when thousands of tons of explosives rained down from the sky, when the most powerful bombs ever created slammed into those roofs, and when the concrete held. The bunker at Bordeaux similarly survived intact and remains standing today. At the Valentine facility near Bremen, the structure proved so durable that post-war plans to destroy it by blasting were abandoned because the explosions would have damaged nearby villages. Instead, the German Navy took it over as a storage depot in 1960. The story of the Disney bomb and the other concrete penetrating weapons developed to attack U-boat pens represents a fascinating chapter in the history of military technology. It shows how warfare drives innovation, how desperate circumstances lead to creative solutions, and how even the most brilliant engineering solutions sometimes arrive too late to change the outcome they were designed to influence. The fact that a weapon, inspired by a Walt Disney animated film, became a real bunker buster used in combat operations seems almost too strange to be true, yet it happened. Barnes Wallis, the genius behind the earthquake bombs, never stopped innovating. His principles of weapons design, emphasizing aerodynamic efficiency, structural strength, and kinetic energy, influenced military engineering for decades after the war. The concept of the bunker buster bomb, a weapon designed specifically to penetrate hardened targets before detonating, became a permanent part of military arsenals worldwide. Modern precision-guided munitions can accomplish what the Disney bomb attempted, hitting targets with accuracy measured in feet rather than yards, and penetrating defenses that would have seemed impregnable to World War II planners. But in 1944 and 1945, when Allied bomber crews prepared to attack targets protected by the thickest concrete ever poured, they relied on weapons that pushed the boundaries of what was technologically possible. The Disney bomb, with its rocket motors and its aerodynamic profile and its ability to punch through 16 feet of concrete, represented the cutting edge of that technology. The crews who flew these missions faced intense anti-aircraft fire from the formidable defenses surrounding the U-boat bases. They flew aircraft modified in ways that affected handling and performance. They carried weapons that were experimental and sometimes unreliable, and they did it anyway because the mission demanded it, and the stakes were too high to do otherwise. The engineers who designed these weapons worked under immense pressure. Every day that passed meant more Allied merchant ships sent to the bottom of the Atlantic, more sailors lost, more vital supplies failing to reach Britain. The U-boat threat was existential. If the Germans could cut the Atlantic supply lines, Britain might be forced to negotiate. Every innovation in anti-submarine warfare, every improvement in weapons technology, every advantage gained could mean the difference between victory and defeat. The Disney bomb emerged from this crucible of necessity. Royal Navy engineers watching an animated propaganda film saw past the fantasy to a real possibility. They did the mathematics, ran the calculations, solved the engineering challenges, and created a weapon that did exactly what it was designed to do. It penetrated concrete that conventional bombs could not touch. It drove through barriers that had been considered impenetrable. It showed that given enough ingenuity and determination, no defense was truly invulnerable. The weapon's late arrival in the war and its limited deployment meant it never achieved the strategic impact its creators hoped for. But in the larger context of military history, the Disney bomb and its contemporaries, like the Tallboy and Grand Slam, represent crucial developments in the evolution of aerial warfare. They demonstrated that hardened targets could be attacked from the air, that concrete fortifications were not the ultimate defense, and that the race between defensive and offensive technologies would continue to drive innovation. The German engineers who designed the U-boat pens created structures of remarkable sophistication. Their multi-layered defensive systems, their Feingrosten and explosion chambers, their attention to how concrete behaves under extreme stress, all of this represented excellent engineering. They built fortresses that stood up to years of concentrated bombing and survive to this day. But the Allied engineers, working with different constraints and different objectives, created weapons that could defeat those defenses when used correctly. It was a competition of innovation, each side pushing the boundaries of what was possible, each advance prompting a counter-advance. If you're still watching, we'd love to hear your thoughts in the comments. Have you ever visited any of these U-boat bunkers that still stand today? What other stories from World War II engineering would you like us to cover? And don't forget to subscribe if you haven't already. The legacy of this technological competition extends far beyond World War II. The principles that Barnes-Wallis applied to his earthquake bombs, the understanding that kinetic energy and penetration capability depend on velocity, mass, sectional density, and structural strength, these principles inform modern weapons design. The concept behind the Disney bomb using rocket assistance to increase a weapon's terminal velocity and penetration capability has been refined and perfected in modern bunker-buster munitions. Today's precision-guided penetrating weapons can do what the Disney bomb could only attempt, striking targets with near-perfect accuracy and penetrating defenses measured in dozens of feet of reinforced concrete. But in the context of 1945, with the technology available at that time, the Disney bomb was revolutionary. The fact that it could penetrate nearly 15 feet of concrete was extraordinary. The fact that it achieved velocities approaching Mach 1.3 without any sophisticated guidance systems or advanced propulsion technology was remarkable. The fact that it worked at all, that engineers could take inspiration from a cartoon and turn it into a functional weapon in the midst of a desperate war, speaks to the innovation and determination that characterized that entire generation. The crews who dropped these bombs rarely knew whether their weapons hit or missed, whether the rockets fired or failed, whether the penetration achieved the design depth or fell short. They released their ordnance, turned away through the anti-aircraft fire, and headed home. The reconnaissance photographs taken after raids sometimes showed damage, sometimes showed nothing but cratered earth around intact structures. The ground truth was often difficult to determine until after the war ended and Allied personnel could inspect the targets in person. What they discovered was that the U-boat pens, for all the effort expended against them, had largely survived. The concrete had held, the multiple defensive layers had done their job. The German engineers had won that particular battle. But the war itself had been won by the Allies through a combination of strategies and technologies, of which the bombing campaign was only one part. The U-boats were defeated at sea in the Atlantic by convoy escorts and long-range patrol aircraft and code breakers and improved sonar. The pens became irrelevant, not because they were destroyed, but because the submarines they sheltered could no longer operate effectively. Still, the development of weapons like the Disney bomb had value beyond their immediate tactical impact. They demonstrated capability, proved concepts, and advanced the science of weapons design. They showed that innovative thinking could solve problems that seemed insurmountable. They proved that even the strongest defenses could be challenged by sufficiently advanced offensive technologies, and they provided valuable data and experience that would inform post-war military development. The story also illustrates the complex relationship between different branches of military service and different national militaries within an alliance. The Disney bomb was developed by the British Royal Navy but deployed primarily by the United States Army Air Forces. British bombers like the Lancaster were carrying Tallboy and Grand Slam bombs against some targets, while American B-17s carried Disney bombs against others. There were questions of doctrine, of target priority, of resource allocation, all the complicated coordination required when multiple organizations with different capabilities work toward common goals. The fact that the Royal Navy developed the Disney bomb but didn't have aircraft capable of carrying it speaks to these organizational challenges. The Navy understood the problem and engineered a solution, but the implementation required cooperation with air forces that had their own priorities and target lists. Getting the weapon into combat use required navigating bureaucratic and strategic complexities that had nothing to do with the engineering excellence of the weapon itself. These are the realities of warfare that often get lost in simplified narratives. The development of revolutionary weapons is only part of the story. Getting them manufactured, getting them to the units that will deploy them, training personnel in their use, coordinating operations, assessing results. All of this requires vast organizational efforts that can be as challenging as the original engineering problems. When we look back at weapons like the Disney bomb from our perspective 8 decades later, it's easy to focus on their limitations. The high rocket failure rates, the accuracy problems, the late deployment, these are all valid criticisms. But it's important to remember the context. This was cutting-edge technology developed under wartime pressure by people working with the materials and knowledge available in the early 1940s. They didn't have computer modeling or advanced materials or precision manufacturing to the tolerances we take for granted today. They had slide rules and wind tunnels and practical testing. They had experience and ingenuity and determination. And with those tools, they created weapons that could punch through concrete barriers thicker than a house, weapons that flew faster than the speed of sound, weapons that seemed like magic to people who witnessed their effects. That's why some people called the Disney bomb witchcraft. Not because there was anything supernatural about it, but because the results seemed to defy what everyone knew was possible. Concrete that had withstood thousands of tons of conventional explosives simply parted before these rocket-assisted projectiles like it was butter, like it was nothing at all. The laws of physics hadn't changed, but human understanding of how to apply those laws had advanced dramatically. What seemed like magic was actually mathematics, engineering, and inspired design brought together in a 17-foot-long package of steel and explosive traveling at nearly 1,000 miles per hour. The U-boat pens themselves remain as physical evidence of this technological competition. Visitors walking through these structures today can see the scars where bombs struck and failed to penetrate, can examine the complexity of the multi-layered roofs, can appreciate the engineering sophistication that went into both the defenses and the weapons designed to defeat them. These are not just historical curiosities. They're monuments to human ingenuity on both sides of the conflict, reminders of what people can accomplish when survival demands innovation. The story of the shell that punched through U-boat pens like butter is ultimately a story about the relentless drive to overcome obstacles. When conventional bombing failed, engineers developed earthquake bombs. When direct penetration was required, they created rocket-assisted projectiles. When accuracy was insufficient, they kept refining their techniques. The fact that these weapons arrived too late to decisively affect the outcome of the Battle of the Atlantic doesn't diminish the achievement they represent. They proved that the seemingly impossible was merely difficult, that innovation could trump even the most formidable defenses, and that the competition between offense and defense would continue to drive technological progress long after the war ended. So the next time you hear about modern bunker-buster bombs or precision-guided munitions or any of the sophisticated weapons that militaries deploy today, remember that their lineage traces back through decades of development to weapons like the Disney bomb, the Tallboy, and the Grand Slam. Remember the engineers who drew inspiration from an animated film and turned fantasy into reality. Remember the bomber crews who flew through flak to deliver these weapons against the most heavily defended targets in occupied Europe. And remember that the massive concrete structures they attacked, those U-boat pens that seemed invulnerable, were indeed penetrated by shells that cut through them like butter, exactly as the title of this story promises.